Welcome back to Algorithmic Game Theory. In the last lecture, we started discussing non-truthful mechanisms, like for example the first price auction. We introduced the notion of a base-Nash equilibrium to formally specify how players might behave in such a setting where they don't know the other players' valuations. Today we'll generalize all of this a bit beyond first price auctions, but we'll also come again across the first price auction and kind of see again the entire argument of why the social welfare in a base-Nash equilibrium of a first price auction is still reasonably good. Before we get started with this, let's quickly recap again the basic definitions of mechanism design. So we have again n players, bidders, or agents. We have an outcome space, and each player has a private valuation function which maps outcomes to real numbers. And also we'll assume today that these real numbers are non-negative, just like we were assuming this for example, the first price auction anyways. Now the bidders report any sort of bids. We're not necessarily restricting ourselves to direct mechanisms now, so this might be just some arbitrary possible bids, which are BI, this is the set of possible bids for player I, and B is just the Cartesian product of these, so this is the set of all bid profiles. A mechanism takes as input a bid profile, maps it to an outcome, this is the so-called outcome rule, and we also have a payment rule which maps a bid profile to a vector of payments. Here it is again important that those are non-negative today. What we were talking about then always was dominant strategy incentive compatibility. This is something we're not doing today. We'll still have the notion of quasi-linear utilities, so the utility of player I under bid profile B when his or her valuation is VI. Then the utility will be VI of f of b. F of b, this is the outcome computed under bid profile B, and from that we subtract the payment that this bidder has to make. As I was saying, we're not discussing truthfulness today. We're rather considering the games that are induced by such mechanisms. And then, for example, we might consider a pure Nash equilibrium. So what would that look like? Although we've seen this a couple of times now, maybe it's good to once again understand what a pure Nash equilibrium means in this context. So we'll be given a fixed valuation profile V, and then a profile of bids B is a pure Nash equilibrium if for every player we have that the utility when bidding BI is at least the utility when bidding BI prime for all possible BI prime. So in a similar way, you could also generalize the notion of a mixed Nash equilibrium, of a correlated equilibrium, or not. It's not even a generalization, it's just an application to the setting. The point is, this is a complete information setting in the sense that this variation profile is fixed. Each player has their fixed valuation profile, and now what we're looking at is a pure Nash equilibrium, and so this means the strategies may even depend on the exact same valuations of the other players. Still, what you could ask now is, what is the price of anarchy? How good is such a pure Nash equilibrium compared to the social optimum? And we can define this also here. So to make this more precise, we'll talk about social welfare of some state, sorry, not of some state, of some outcome. This will be taking the sum over all valuations of the respective players. And then we can say opt of V, that would be the maximum social welfare that we could see. And also we could write down the social welfare of a mechanism M under bids B. This we would now write as social welfare with a subscript V. So I should also say that this depends on the valuation profile. And then we would now write this down as take the sum over all players and see what the mechanism computes under bid profile B, and then of course evaluate it regarding the actual valuations V. You can also write this in a different way because we have the quasi-linear utilities. You can also write this down as the sum of the utilities plus the sum of the payments. And now we can also define the price of anarchy. We'll do this exactly as before. So the price of anarchy for an equilibrium concept EQ would be take the worst of these valuation profiles. Now take the worst of the equilibria and compare the optimal welfare that is possible with this valuation profile to the expected welfare at equilibrium. And here again, EQ of V, this is a set of probability distributions Of course, now it depends on V, what is a pure Nash equilibrium or a mixed Nash equilibrium or whatever. And this ratio will always be, of course, at least 1, because the optimal social welfare is, of course, at least as good as whatever the mechanism can do. It will be smaller for a pure Nash equilibrium than it is, for example, for a mixed Nash equilibrium, than it is for a correlated equilibrium, than it is for a coarse-correlated equilibrium. You can do exactly the same things here. One thing that makes this a little more difficult is that you also have always these variations V floating around. But for the time being here, we just say, okay, they are just fixed. Everybody knows the variations, and then this is just an induced game. And this way it is like everything that we've seen up to this point. What might be a little different is the definition of social welfare. So I might want to spend one more minute talking about this, because why are we also taking the sum of the payments as social welfare? Why is this part of our definition of social welfare? Because we understand that the mechanism designer is also participating, or the mechanism is also a participant in this game, so the money isn't actually lost. It is okay also to, if for example the mechanism is getting a lot of money. This would all be for the full information setting. But we can also do the same things now for incomplete information, for which we now have a great equilibrium concept, namely the base Nash equilibrium. So for incomplete information, we'll now have that each variation is drawn from a distribution di independently. These di are public knowledge, but the vi, those are private. And for that, we now have the base Nash equilibrium. More precisely, it is a pure base Nash equilibrium. I guess you might have an idea of what a mixed base Nash equilibrium is, how you might define that. But we'll not cover this here. So a pure base Nash equilibrium, this is a profile of bidding functions beta I. Beta I maps from Vi to Bi, so maps a variation to a bid. And now the property is that for all I, for all Vi, and all Bi prime, the expected utility, when we now draw the other players' values from the distributions, and now everybody's playing according to beta, this will be at least as much as if we are unilaterally deviating to B prime instead. And still, this is all for a fixed value Vi. So Vi is fixed, we know our own value, but over the other values, we take the expectation. Also here we can now define the price of anarchy. just as we know that. So the price of anarchy for base Nash equilibria, how would you now define that? You would now say, okay, this is the maximum over all distributions D, the maximum over all beta that are base Nash equilibrium, and then you take the expected social welfare of the optimum and you compare it to the expected social welfare at equilibrium. How do you do that? So let's first talk about this part here. For a fixed distribution, or we now have a distribution for each of the players, we combine these by writing D. We now draw from each of the distribution ones and we take the optimal social welfare and what's the expected optimal social welfare. That's the one question. And what do we compare this to? We compare this to the expected social welfare in our equilibrium. So draw from the distributions D and now take beta of V. How big is your, what are the players bidding? And now you run the mechanism. I should also not forget to write here the subscript V, because the social welfare, of course, is only defined for given any valuations, because it depends on the valuations. So this is the ratio of, for this particular equilibrium, how much welfare are we losing compared to the expected optimal welfare. This is only comparing the two expectations. Then we take the worst of our equilibria by taking the maximum of these ratios. This ratio will always be at least 1. And also we take the worst of these distributions, which is like what we did for the full information setting, where we said, okay, take the worst of these valuation vectors. So once again, what makes this complicated is that V is a random variable, so opt of V is also a random variable. And what we're doing here is we're comparing just the expectations. You could also do something else. You could maybe take the expectation of the ratio, things like these. That's also something that you might want to try, but at least the techniques that we're seeing today do not succeed with this. We've already seen that the price of anarchy for base Nash equilibria of a pure of a first price auction is at most 2. And what we've used is a very general technique, which we'll get to know today, namely that the first price auction as a mechanism is smooth. Before we come to the definition of a smooth mechanism, let's recap how we showed a price of anarchy bound for the first price auction. How did we do that? We showed that the utility, when you bid half your value, the others are bidding something, we don't actually care, is at least half your value minus the maximum bid of anybody. And also, when you bid half your value, then you will never get a negative utility, because either you get the item but then you're paying only half your value, or you're not getting it. So this holds for all B and all V. And of course, all players. How does one show that? This followed by a simple case distinction. Because either you're now outbidding the maximum bid, then VI over 2 will be at least the maximum bid. And then your utility will be your value minus half your value, so then it will be this much. Or it might be that you're bidding below the maximum bid, then your utility will be 0, and this is negative. So this is how you make these arguments. Good. What does this give us in combination? So in combination, for all B, for all V and all B, we now have the following inequality. Take the sum of the utilities when now everybody unilaterally deviates to half their value, the other bids remain unchanged. Then this will be at least the maximum of these utilities. And because all of them are non-negative, and we'll have here V over 2 minus the maximum of all BI prime. Good. Now, what are these things? This here, this is exactly equal to a half times opt of V. And this here, this is exactly equal to the sum of the payments under bid profile B. Because in a first price auction is really simple in terms of the payments, because that is just the payment that we're seeing. And here, the maximum of VI over 2, this is just half the maximum value. So what does this mean for the price of anarchy? For a pure Nash equilibrium, B under valuations V, we now have that the social welfare is equal to, yes, don't forget, it's the sum of the utilities plus the sum of the payments. And this will be at least the sum of the utilities after each player is now unilaterally deviating to have their value, plus the sum of the payments. And in combination with our inequality above, this shows that this is half the optimum value. Good. Now this is exactly the kind of proof that we'll generalize now. We will generalize precisely this inequality. Whenever this kind of an inequality is true, then we call the mechanism smooth. What does this look like? This is the smoothness framework For mechanisms, we've already seen smoothness of games, which relates to this in a pretty clear way, although the notion of smooth games doesn't quite model what we want to do here, because we kind of have these mixed sign objectives because we're also subtracting and again the payments. So this is why people came up with this definition, which is more tailored to the mechanism setting, which is now the following. We'll have lambda and mu, which are non-negative. And we now say that a mechanism M is lambda comma mu smooth if for all V and for all I, so for every valuation profile and for every bidder, there is some BI star such that for all bids B, the following holds. Take the sum of the utilities where each player now unilaterally deviates to their BI star, the other players don't do that. And then this will be at least lambda times opt of V minus mu times the sum of the payments under B. So what does this mean? This now means that for any valuation profile, we now have that we can say there is a safe bid, BI star for every player, with the following property. Now, for every bid B, the sum of the utilities after these, when each player is now deviating unilaterally to BI star, to their safe bid, this is at least lambda times the optimal social welfare minus mu times the sum of the payments. This could look familiar because let's go back to the first price auction. There we showed that for all V and all B, the following inequality holds: Vi over 2, utility when everybody deviates to Vi over 2, this is at least a half times opt minus the sum of the payments. And this Vi over 2, this we can now call BI star. And if we call this BI star, then this is exactly the kind of inequality that smoothness is asking us for. One important thing also happening here, this Vi over 2, so this BI star, this does not depend on B. And this is also a little implicit in this definition that BI star may not depend on B because this has to hold for every possible B. So this is our first observation. A single item first price auction is a half, 1 smooth. But what about other mechanisms? What about the second price auction? The second price auction indeed is not smooth, but there's another auction format which we might consider here, namely the all-pay auction. What's the all-pay auction? In the all-pay auction, not only the winner pays his or her bid, but everybody does. This sounds spectacularly ugly because not everybody, regardless of how much they were bidding, has to pay, but it is still a reasonable auction format to understand and to compare to the first and second price auction. It is certainly not truthful, because if you know that for sure you won't win, then you definitely don't want to bid anything because you will only pay for this. And what can we show for that? A single item all pay auction is a half, 2 smooth. How would we show that? What do we now have to show? We'll have to show that for every bidder there is a good bid. And interestingly enough, these deviation bids, those may depend on the valuations. And not only my own valuation, but the valuation of everybody around. And this allows us to now define the deviation bid bi star as follows. We let J be a bidder with highest value Vj. And we now set bi star to be Vj over 2 for this bidder, and for all other bidders, they are not bidding anything. And now consider an arbitrary bid profile B. What's now our claim? Our claim is that Uj of Bj star, B minus J, this will be at least half his or her value minus 2 times the maximum of all other bids. Why that? What can happen? First case is, so I'm now in this all-pay auction, and in this all-pay auction, I'm now the bidder of value Vj, and I'm bidding half of this value. What can happen? Either I win the item or I don't win it. Regardless of whether I win the item or not, I'm always paying half my value. So the first case is bidder J wins the item in Bj star, B minus J. What will then be the utility? Then the utility will be exactly equal to half his value. And then in the other case, what will happen? Well, then the utility will be equal to minus a half times Vj, because this is how much he or she is bidding, but they're not winning the item. But the maximum of all other bids has to be at least half times Vj. So this means if we combine this, that also then the utility will be at least a half times Vj minus 2 times the maximum bid. So this already shows this bound here on the utility when, so I'm the one with the highest value in the all-pay auction, I'm bidding half my value, then my utility will be, after this deviation, will be at least this much. Then, what happens for all other players? There we'll have that the utility, after deviating to, okay, they're deviating to 0. By the way, I forgot to write down here everywhere that this is, of course, depending on Vj. So now, let's not make the same mistake again. They now bid something else, but they always bid 0, so they are getting no utility. We can even make this an at least to make sure that maybe they are even winning when they're paying nothing. Even that could happen if everybody's bidding 0. So definitely the utility of the ones who are bidding 0 will be non-negative. So if we combine this, then we're getting that the sum of the utilities after deviating, after unilaterally deviating, will be at least a half times Vj minus 2 times the maximum of all bids. And this is at least a half times Vj minus 2 times the sum of the payments. Here now, in this all-pay auction, suddenly the sum of the payments isn't equal to the maximum bid, but it's rather equal to the sum of the bids. So this is an inequality now. But other than that, it is what we've seen before. And so we're getting that this is equal to a half times opt minus 2 times the sum of the payments. So this concludes our proof. Once again, how did this proof work? We said, okay, the one with the highest value should bid half this value. The others shouldn't bid anything. And now we know that the one with the highest value will either have a high utility after this deviation, or we know that the sum of the payments before must have been big. And for the other players, we don't use anything. They just say, okay, they say we are not bidding. So usually bidding half your value is a good idea for all these smoothness proofs. What we'll do next is we'll try to understand how this now implies a bound on the price of anarchy. And you've already seen this a bit shining through here, that what will the argument be like? The argument will generally be like either whenever you bid your safe bid, your safe deviation bid, it either happens that you win and you have a high utility, or before the sum of the payments must have been high. But if the sum of the payments must have been high, this means something, because this means that in the equilibrium there has to be a high welfare, because the sum of the payments is part of that. So far, we've seen the definition of a smooth mechanism, and now we'll show that smoothness of a mechanism implies a bound on the price of anarchy, and we'll first consider the case of only full information, and more precisely, we'll only talk about pure Nash equilibria to keep things really, really simple. Then afterwards, we'll talk about the more interesting part, namely base Nash equilibria, where things aren't quite as straightforward. But let's start with these pure Nash equilibria. What's the theorem? This, by the way, is by Jakanis and Tardosh from 2013. So much younger than many other things that we've seen so far. If M, so if a mechanism M is lambda mu smooth, and players have the possibility to withdraw from the mechanism, then the price of anarchy for pure Nash equilibria is at most the maximum of mu and 1 divided by lambda. How will we prove this? We will now, just in any price of anarchy proof, we will now say, okay, consider a pure Nash equilibrium. Now, it is not beneficial for any player to deviate to, and then we use the fact that this is a smooth mechanism, so it is not beneficial to deviate to your safe deviation bid, and then we just use the smoothness inequality. More precisely, let B be a pure Nash equilibrium. Then ui of bi, b minus I, vi is at least ui of bi prime, b minus I, vi for all I and all bi prime. In particular, this holds for bi prime being equal to bi star, so a safe deviation bit. Then what we're getting is that the sum of the utilities, when they are bidding bi, the others are bidding b minus I, and their value is v, this will be at least the sum of the utilities if they unilaterally deviate. And now for this we can use the smoothness inequality. So this will be at least lambda times opt of v minus mu times the sum of the pi of b. So what does this tell us for the social welfare that we're seeing? The social welfare will be at least lambda times opt of v minus mu times the sum of the payments plus the sum of the payments. Good. Now what happens? Now it can happen that mu is at most 1. Then what we're seeing here is at least lambda times opt of v, and this is exactly what we were looking for. Now there is also the option that mu is greater than 1, which was, for example, true for our all-pay auction. In this, we had mu being 2. Then we'll have to go through one more argument, namely, we'll have that ui of b is equal to vi of f of b minus pi of b. And this will have to be 0 because players can withdraw from the mechanism. In the all-pay auction, for example, they can withdraw by just bidding 0. So this then means that pi of b is less than, or is at most, vi of f of b. I'm never paying more, in equilibrium, I'm never paying more than my value, or in other words, I always have negative utility, non-negative utility. Good. What does this tell me? This gives me a bound on this here in the inequality. So therefore, the sum of the vi of f of b, that's what I was having here, is at least lambda times opt of v minus, or rather say plus 1 minus mu times the sum of the vi of f of b. And this now tells me that the sum of the vi of f of b will be at least lambda over mu times opt of v. And this proves also the claim for this case. Great. So, how does this work? This works just as I was stating before. Players don't want to deviate from what they're doing in the equilibrium. There is this safe deviation bit which they could bid instead, but that won't make them happier. At the same time, if they were bidding that, we would have a lower bound for the utility. And then we just mess around with the inequalities and get where we want it to go. This, I hope, looks very familiar to the smoothness price of anarchy bounds we got for smooth games quite a while back. You could, in principle, also do this for mixed Nash equilibria, correlated equilibria, coarse correlated equilibria. This would all look exactly the same. But this won't look exactly the same when we're then moving to base Nash equilibria. And base Nash equilibria, this is actually the kind of equilibria that we want to now talk about, because we don't want to assume that all players know all other values, but rather that they only had these prior beliefs about them. After having now seen how we can bound the price of anarchy for pure Nash equilibria via smoothness of a mechanism, we will now do the same thing but for base Nash equilibria. We've already seen one argument to bound the price of anarchy of a base Nash equilibrium, namely for the first price auction. And for that first price auction, we showed that deviating to half your value is actually never a bad idea, and then we just matched up the inequalities and everything worked out quite fine. Now we'll show that actually everything that we need is smoothness of the mechanism, which just means that there is this deviation bit, and then it will be really important that these deviation bits don't depend on the other bits right now, but they only depend on the valuations. What makes things a little complicated is that the deviation bits may depend not only on your deviation bit may not only depend on your own value, but also the other player's values. Don't forget that's something that we use to prove smoothness of the all-pay auction. Only the one with the highest value is deviating to something non-zero, so only that guy is bidding something. The others, they are bidding nothing. And this seems to be crucial, but this also seems to be weird. If we're now talking about a base Nash equilibrium, how the hell am I supposed to do this? How the hell am I supposed to know if I now have the highest value or not? Because if you now tell me whenever you have the highest value, then bid half your value. Whenever somebody else has a higher value than you, don't do that. I cannot do this. I cannot do this in a base Nash equilibrium just because I don't know the other player's values. However, there is a really smart way around this, and this is what we will see now in the proof of this theorem. So what's the theorem? If a mechanism M is lambda comma mu smooth, and players have the possibility to withdraw from the mechanism, then the price of anarchy for base Nash equilibria is at most maximum of mu and 1 divided by lambda. So as I was pointing out, V star may depend on V, so we'll always write the exact dependence of V as Bi star of V. Now the magic happens. Let V tilde be any valuation profile. If now beta I is at base Nash equilibrium, then what we have the following. We'll have that the expected utility when I now bid according to this base Nash equilibrium, this will be at least as much as my utility when I bid according to this deviation strategy. So this will be Bi star of Vi. I know my own value, but I don't know the other values, so let's just use V minus I tilde instead. And of course the other players still keep playing. According to beta. That's something, that's a deviation I could make because, okay, V tilde, that's just something that I've just invented. I couldn't write at this point Bi star of V because I don't know V. But I know this V tilde because that's just some valuation profile I invented. Okay. This holds in particular if I now draw V tilde from the known probability distributions. So now draw V tilde from d1 through dn independently, and also take the expectation over Vi, because so far this was true for every Vi. So now we'll have the expectation over V and V tilde of the utility in the base Nash equilibrium of player I. This is at least the utility if bidder I deviates to Bi, Bi star of Vi, V minus I tilde. By the way, here I'm now taking the expectation over V tilde, although this doesn't depend on V tilde. So I might or might not write the expectation over V tilde because it doesn't matter. v tilde doesn't even show up in there. Good. And now we really come to the magic. Because what was the thing about v tilde? Player I was not just saying, okay, I'm certainly not gaining anything by the falling thought experiment. I now draw this v tilde and this v tilde, and then I take my bi of vi comma v tilde. But the way this v tilde was drawn was exactly from the same distributions that are known. So what we might also do is we might say swap now v and v tilde. These are, or more precisely, swap v minus I tilde with v minus I. Because those are identically distributed random variables. And this is still mysterious, but let's first write this down. Because v minus I and v minus I tilde are identically distributed, what are we getting for the right-hand side here of this inequality? The utility when I now bid bi star of vi comma v minus I tilde, and the others are bidding according to v. My value is vi. This is exactly the same as when I now swap v minus I and v minus I tilde. So I'll get here bi star of v minus I of v tilde. Note that b minus I of v does not depend on vi, because that's only the other player's bids and they don't know our value. And now we are here. And this is something that actually is interesting, because now we are suddenly doing the good bid against these valuation profiles, but the other players are now suddenly stupid, because they are bidding according to if their valuations were v tilde, although they are actually v. Okay, but we are now doing the right thing, they are doing something weird. But now we can combine these, and in this we can actually apply the smoothness inequality. So more precisely, we now have the following. We now have that by smoothness, the sum of all ui of bi star of v comma beta minus I of v tilde comma vi, this will be at least lambda times opt of v minus mu times the sum of the payments. And this holds also if we take the bid profile b of v tilde. So if we now combine these things, if we now combine this here with this, we can use linearity of expectation. So what we'll be getting is that the sum of all these expectations ui bi star of v, comma beta minus I of v tilde, comma vi, this will be at least lambda times the expectation of opt of v minus mu times the expectation of the sum of the payments if bidders bid according to beta, but their valuations are v tilde. And now, this is something that we've already seen, because this is something that we can compare to the expected utility of bidder I. So this is at least the expected utility of bidder I in the equilibrium. There this was coming from. Here, this is now the expected sum of the payments if the bidders are bidding according to beta, but their true values are v tilde. But nothing is holding us from reversing back and swapping again v and v tilde, because they are still identically distributed. So this here is nothing but the expected sum of the payments when bidders are bidding according to beta and the true values are v. So if we now combine all of this, we'll have that the sum of the expected utilities when everybody's bidding according to beta, true values are v, this is at least lambda times the expected optimum of v minus mu times the expected sum of the payments. And somehow miraculously, all this v tilde vanished again. Because here v tilde never actually occurred. Here v tilde we saw, okay, we can again swap to v. And so all that we're getting from here is now the following statement: the sum of the expected utilities is at least lambda times the expected optimum minus mu times the expected sum of the payments. And this is exactly the kind of inequality we had before in a pure Nash equilibrium, although there without these expectations. But there we had the sum of the utilities is at least lambda times opt minus mu times the sum of the payments in the equilibrium. There it is really straightforward to get this inequality. Here it was a lot of work and somehow mysterious. But from this point onward, we can work exactly like we did for a pure Nash equilibrium. How so? We are getting that the sum of the expected values that the bidders have when they bid according to the equilibrium. This will be at least lambda times the expected optimal social welfare minus mu times the expected sum of the payments plus, again, expected sum of the payments. We're using linearity of expectation here so often, I sometimes forget to even mention this. So this was also, again, due to linearity of expectation. Good. And where are we now? If mu is less than 1, or at most 1, this implies the claim. And what if mu is bigger than 1? Then again use that ui of beta of v will be at least vi of, this is equal to vi of f of beta of v minus pi of beta of v, but we assume that this is non-negative because players can withdraw from the mechanism. So this again means that the expected sum of the payments is at most the expected value that we have and if we now move all of this together, then we see, okay, mu times the expected sum of the values is at least lambda times the expectation of opt. And this means exactly what we were claiming, that the expected social welfare of beta is at least lambda over mu times the expectation of opt of v. And we are done. So the things you should always keep in mind are actually two main insights. The one thing was, how would you do this in this full information setting? How would you follow this proof in the full information setting? There it's actually quite straightforward because bidders cannot benefit from unilateral deviation to what we said their safe deviation bids are. And then there was the magic happening in this proof where somehow the bidder could hallucinate the other bidder's values, and somehow by linearity of expectation and because they were identically distributed, we could swap all of this. This is a magic trick, but it does appear frequently, and therefore I'm happy to have already shown this right here. I guess we'll see this again later, this semester. Then the point was, after the swap, suddenly the situation was, I'm the one who's actually bidding the correct way. You are somehow hallucinating everything. You don't actually even see your true values, you are hallucinating your values and bidding according to these. But in this inequality, and that may be a little confusing at first sight, here we are not talking about the other bidders. Here we are only saying, okay, the other bidders might now bid according to their hallucination. But when we then apply for them the utility bound, of course we don't pretend they are hallucinating, but the others, it is always the others who are hallucinating. And this is somehow due to a linearity of expectation, because we can bound each of these, or we can see the equality for each I separately, and also because V minus I was independent of Vi, and also Vi minus I tilde was independent of both Vi and Vi tilde. And this is somehow something that you might have to digest a little more. Feel free to go over the proof once or twice again and see how things actually work out. But eventually, the important thing is that we have to do this in one way or another. For example, for the all-pay auction. So now we also have a price of anarchy bound for the all-pay auction of, what is it actually? Our lambda was a half, our mu was 2, so we'll have a price of anarchy bound of 4 for the all-pay auction. Next time we'll continue with this, and fortunately then we don't even have to talk about Base-Nash equilibria anymore, because we have this theorem, and this theorem is everything that we need. In order to then bound a price of anarchy, all we have to do is show smoothness. And all this smoothness, that is not talking about these probability distributions. It's not talking about strategic behavior, it is just showing some property of the mechanism. And this is really good because it allows us to actually separate the argument into two very disjoint parts. And if you now wanted to show a price of anarchy bound, probably you should show smoothness. And the same thing, by the way, also holds for smooth games, that you also want to do the same thing. And then the rest somebody else does for you. And this then holds for every possible equilibrium concept you might imagine, or maybe not. Then maybe you have to have a closer look at what kind of smoothness you're showing. But general rule of thumb is to show a price of anarchy bound. The first thing that you should try is you should try to prove smoothness. Once again, if you have any questions, please do reach out to me. And I'm looking forward to the next time. Stay safe until then. Bye.